Landrø is a professor and leads the Centre for Geophysical Forecasting at the Norwegian University of Science and Technology. He's a member of the European Association of Geoscientists and Engineers and the Society of Exploration Geophysicists, the Norwegian Academy of Technological Scientists, and the Royal Norwegian Society of Sciences and Letters. That is a mouthful. You're a part of everything. But I think the main point today is that you're leading some incredible work on DAS and are going to talk to us about some of like the true you're at the forefront of pushing the boundaries of what we can do with acoustics and sensing the marine environment. So I think you're going to lay some groundwork for us for where innovation is going in that space. So Martin, I'm going to hand it over to you. Take it away.
Thank you very much. Let me see. This slide shows you a map of from Svalbard, north of Norway, and it's this is our main lab, I would say. We are using 2 fiber optic cables that were deployed in 2015. Entirely for the purpose of telecommunication between Ny-Ålesund, which is a small research facility. It's most of the researchers who live there, 40-50 people live up there, to the bigger city called Longyearbyen down here. The distance is 256 kilometers. And in 2015, as I said, the government in Norway decided to spend a lot of money to connect these 2 cities via 2 fiber cables. And we are allowed to use these fibers for also for sensing. And we are used so since 2020 approximately. So this is our main lab. So what you see is the 2 fibers, approximately 250, 260 kilometers long. They are trenched into the seabed, approximately 1 meter below seabed. There are 2 because they wanted to have like a spare one. The depth profile is shown on the bottom. So you see for the blue and the black cable. So it's it goes down to almost 400 meters, but it can be shallow, like 60, 70 meters also. So in this area, we have a lot of whale activity, and that was our main focus actually when we went up there in 2020 to do recordings. This is just the same figure, but seen from a map view. So Ny-Ålesund, this small city, is here, and the cable is diving into the water here, and goes fairly deep in the beginning, and then it climbs onto the shelf here, west of the island called Forlandet, and then it goes south, and then into the fjord called the Ice Fjord, which is shown here. So that's the track of our laboratory. So the nice thing about this is that we can continuously monitor 256 kilometers by using the distributed acoustic sensing. So for those who are not familiar, this is a slide that summarizes the principles. What you need to do a DAS recording is this interrogator, which essentially is a laser source, and a big computer to store all the data. We store approximately 4 to 7 terabytes per day. So it's a lot of data. It's an enormous amount of data. The principle is that you send in a beam, a light beam, into the fiber. And if you have an acoustic signal that is close enough to the fiber, then the fiber will stretch a bit. This stretching is typically of the order of nanometers. It's very small, but since you are using light, we can use cross-correlation techniques as it's hinted up on the upper right here to find out where this sound hit the fiber, and also the strength, how strong was this sound. So that is what we are using to monitor a long distance. So we measure typically every 10 meters, every 5 meters or so. We can design that in the interrogator. So we can also decide in the interrogator which frequencies we want to listen to. For long fibers like this, we are currently, the technology has a maximum, I would say, of 1 kilohertz typically. So that's the principle. So this is an early work was published by Lea before 2022. So what we tested first was, could we see ships that cross the fiber? So to the upper left here, you see a ship that is the AIS position or the GPS position of the ship is the red line. So that's the truth. The black line here is the fiber, and the numbers in black is the distance from the interrogator. So it's 86 kilometers away from the interrogator. And the white dots shows our estimate of the ship based on the fiber only. So this means that we are able to reconstruct the track of this ship within, I would say, 1 kilometer before the ship crosses the fiber, and also 1 kilometer after. We can also see, as you see on the lower left figures here, that we can measure the Doppler effect when the ship is moving towards the fiber and away from it, like an ambulance that you hear in the street. The sound is changing a bit. The Doppler effect is very minor here. It's 0.1 hertz or something, but despite some noise, as you see here, we can still see it. To the right, we come to the whale listening. So to the upper right, we see blue whales at 36, 37 kilometers away from the interrogator. And they are beautiful hyperbolas that you see here. And at 39 kilometers, you see another whale, probably a fin whale, at vocalizing at approximately the same time. The horizontal scale here is 90 seconds, 1.5 minutes. So if I'm lucky now, I can play. Oh. So what you hear here is the reconstructed sound from the blue whale. The strongest signal was at the beginning, up and down shape, and we have multiplied the frequency by a factor of approximately 3 to make it more hearable for the human ear. So we are able to reconstruct the sounding based on this fiber optic cable that is buried below the seabed, and reconstruct the sound track of whales. We can even use the signal from the blue whale and use, again, cross-correlation techniques to make an image. So this is a typical what a geophysicist like me like to do. You make images of the subsurface. So what you see here is that you get first at the fiber, the red line here is the direct arrival from the blue whale. The orange line is the first reflection from the seabed. That has been reflected from a layer below the seabed. So if you see this cartoon to the upper left here, you see how that event has been going down maybe 100, 200 meters below seabed. So that's the second reflection, and then you get multiples and so on. So in this way, we can construct, we think, almost like construct an image of the subsurface using the blue whale as a seismic source. And the interesting thing for me here is that the blue whale has sufficient energy and sufficient voice to see at least 100 meters, maybe 200 meters below seabed. So the blue whale has the ability to discriminate between, for instance, sedimentary rocks at the seabed and basaltic rocks or bedrocks, if you will. A bit more technical here. What we'd like to do is to track the whales. And we know the position of the fiber. We know the depth of the fiber, so X and Y is unknown. These are the position of the whale, X and Y. Z is the depth of the whale, and X and Y here are known. So this is very similar to when we determine the position of an earthquake. It's the same thing. We have a zone or source, and then we use techniques like this, inversion techniques, to determine the position. So in this way, we take the data and we are able to find out where the whale is. So this is done in an automatic way. And in the case when the whale stops to vocalize, and that is one example that we show here, then the uncertainty ellipsis that we compute increases. And then we see that we are just doing extrapolation, which is wrong. So you see this straight line here, this stars. But then the whale actually appears to the left in the figure, but it's inside the ellipsis of uncertainty, so we find it again. So then we continue to track it. So in this way, we are able to follow the whale when if it's not stopping to vocalize for too long period. Yeah, these are just examples of how it looks like on the dust data for various. Here we have 2 fiber optic cables, inner cable and outer cable. So we see 3 fin whales vocalizing at the same time. This is the sound profile again, and we can identify where they are. So by looking at this in real time, like we see here, the red dots that you see are when a whale is close to the fiber. So there, for instance, and then you see the signal at both fibers, but at the delayed time of the other fiber. You see one there. So in this way, we were able to record and track the positions of up to 8 whales. This was fin whales at the same time for a period of 5 hours. So that's where we are today. That's what we think is possible. So the next step is then to do this on a yearly, to extend this in a more massive type of analysis. It's an advantage to have 2 fibers as we have here, because you have it's easier to do the inversion to find the exact position, to avoid what we call the mirror problem. So this is a summary of our analysis so far. Here we have baptized each whale with from A to H here. So we see that, for instance, whale B started approximately here and slowly moved along this path and going almost westernly. And then we kind of lost contact with this whale after 2 to 3 hours. The color bar at the top here is the time in hours. So it's from 0 to 5 hours. Whale D here we see goes south, close to the fiber, makes a turn, and goes back, and so on. Some of the whales seems to be stationary for more than 4 or 5 hours, but vocalizing now and then. The limitations here are, we would say, it's shown by this dashed white line. So it varies with the distance from the interrogator. So at when it's come like 100 kilometers away, we lose accuracy. But typically you can say that maybe 5-10 kilometers from each side, we are able to find these whales. And we can estimate the direction and the speed and so on. When we have the track, we can actually analyze a lot of things. So I think that's it.
I think Bevis captured kind of the feeling in the chat by saying, like, wow, this is incredible research, and they've never seen existing infrastructure used so effectively and creatively. So I think that captures the general mood of the chat and just excitement and interest in what you're doing. I'm going to throw to, I think I'm going to throw to Ord first. Is that right? Yes. Ord, do you want to jump in and ask your question? You jumped in first.
Yeah, sure. Thanks a lot for this wonderful talk. So I'm wondering about the timeline between the data collection and the data analysis, and if you're interested in knowing the new real-time location of the wave. So, yeah.
Yeah. So presently, as you saw on when I showed the plot where you see these events along the fiber, you get an impression of where the whale is, but not exactly. So to find that exact positions, we need to run like a grid search or an inversion, mathematical inversion. And that we cannot do online today. That requires high performance computers, but we are working on that. And the key word here is probably edge computing, that you within close to the interrogator, you analyze the data and try to find out as quickly as possible where the whale is. But we are not at that stage yet, I would say. But that's definitely a goal, and that we want to pursue. So it's a lot of challenges there.
Yeah, amazing. Thanks. Very interesting.
Carlos, do you want to ask your question?
Hi, yeah, sure. Hi, Martin. Thanks. I was just wondering whether this has been used in other contexts within sort of terrestrial environment, and whether there's sort of amplitude and frequency constraints that enable that, or whether it's quite limited to sort of the marine.
Yeah.
Very
So far, it's possible to, as I said, it's possible to go up to 10 kilohertz or even 100 kilohertz, but then you have to limit the length of the interrogating length. So typically, if you have 10 kilometers of fiber, then you can probably go up to 10 kilohertz. So you can, for instance, listen to humpback whales and things like that. But presently, this is also a challenge, I would say, to have high frequencies and long distances at the same time. We are not that yet. We are not there yet. But it's an enormous challenge, of course, because you want a lot of data at the same time. So for terrestrial use, we have tested it close to railway and tried to test if you can see, for instance, a moose that gets close to the railway track to give a warning. It's much easier to detect persons. A walking man is much easier than a big moose, Norwegian moose. It turns out, so that's more challenging, I would say. But there are, of course, a lot of terrestrial uses that are easier in a way than if you go offshore. It's because then you can just put out your fiber for a short time or period, and we have done a lot of tests like that. So that's yeah.
Pete, it sounds like you wanted to jump into that conversation.
Just had a question.
Or are you jumping the queue? Are you jumping the queue? All right, you can jump the queue. Go on.
Sorry, I didn't intend to.
No, you're fine.
Actually, it's a direct question about the terrestrial application, because I know that the sheathing on fiber that's being used for underwater runs and the acoustic impedance between the ocean water to the sheathing to the fiber itself, that's a much more direct continuum in the same order of magnitude for acoustic impedance. But for terrestrial, are you actually picking up more of surface wave stuff insofar as whatever the medium is that you're connected through through some sort of acoustic grounding? Like if this is on a telephone pole or running underground, are you actually getting more transmission of sound through solids rather than through air? Because I'd imagine that the air to sheathing impedance is significantly higher.
Yes.
Just wondering.
That's correct. So I fully agree with what you said. It's for terrestrial use, it's the surface waves we are picking up. So if you have footprints like animals in contact with the earth, then you get that fairly strong signal. But only acoustic signal through air is a bit more challenging, but it's not impossible. But it's weaker, as you said.
Wonderful.
Thank you very much.
That was a clarification of our facilitation. If Pete, you did exactly the correct thing. If you want to add something to the live conversation, put your hand up and I'll call you. But if you want to if you have a question that's like on a different track, put it in the chat and I'll call on you there. One last question, I think, maybe two. Xavier, did your question get answered in the talk?
So I think it was, yeah. So that and Leah replied also about the frequency signal. So I think we.
You're good. Okay. Aoife, did I get your name correctly first? But I think you have our final question.
Yes, you nailed it.
Yes.
Thank you. Hi, Martin. That was a really cool talk. I'm actually a geophysicist by background, so I've read some of your papers on 4D seismic, so really enjoying this. I was wondering, you know, wells are not always vocal creating strain waves anyway. Are those just way too low amplitude to be able to pick up the strain waves from their movement?
Can you repeat that? What was the weak amplitude you say?
Sorry, I think my network connection is not great, but I was wondering whether it would be possible to detect whales when they're not vocalizing from the strain waves that are coming from them moving through the water.
I would hope so, but presently we are not. We are far from that. I think we are dependent on whales to vocalize, and more subtle signals, like you mentioned now. I think we have to be, that's in the future, I would say, because there are background noise and there are challenges here that we, even to detect ships that you might think we make a lot of noise, it's actually often difficult, especially if you're far away from the interrogator. So it's not that, it doesn't solve all the problems, certainly not. So you need a certain signal to noise ratio to detect. But maybe in the future, we become more sensitive. So the current range is, as I said, 100, 120 kilometers, but there are developments in this interrogator technology that makes this possible maybe in a few years to have covered 200 kilometers and so
on. Okay, cool.
Thank you very much.
Okay, you've got a few more questions coming in from Chris and Carly about scalability and concerns from the Navy, but I'm going to wrap the discussion up here, and Martin, you can pop into the chat and pick up those questions there.